Welcome everyone. Today I'll be working a homework problem involving the heat equation and rectangular coordinates. So come inside with me where it's warm and we'll get started. Okay, let's work D1, problem D1. In this problem here, what we have given is a rectangular wall. The temperature distribution is given by this equation here. A plus bx plus cx squared. Now A, B, and C are all constants. One's equal to 900, one's equal to 300 Celsius per meter, and C is equal to minus 50 Celsius per meter squared. So for example, if you took a thermocouple or some device that you could measure temperature with, and you were able to measure the temperature at different locations in your wall or your rectangular object, and then take those temperatures and curve fit it using Excel or something similar to that, you would just get a simple equation like this. Okay. Now something else is going on in this wall is that we have generation. So we're also generating heat at 1,000 watts per meter cubed. This triple prime here, that means per volume, per length cubed. Okay. The area of the wall is given 10 meters squared. The density is given 1600 kilogram per meter cubed. The conductivity is given 40 watts per meter Kelvin. The specific heat is given 4 kilojoules per kilogram K. And here's what we're asked to find. Q dot in at x equals 0, Q dot out at x equal 1 meter, and Q dot stored. And then part C says find the change in temperature with respect to time at x equals 0, at x equal 0.25, and at x equal 0.5 meters. Okay, so they just want you to do the same thing at different locations. Alright, so our geometry, our schematic here, we just have a plain wall. We've got Q dot coming in. We've got Q dot going out. And we have Q dot being generated. This will be at x equal L. That would be at x equal 1 meter. Okay, so for part A, what we know is that Q dot in is equal to minus K times the area times dt dx at x equals 0. Now we know that from Fourier's law. So what we're going to do is take a dt dx of this the temperature profile that was given. So if you took this equation here, took the derivative with respect to x, you would get this right here. dt dx is equal to a b plus 2cx. Okay? And then if we say, well, at where x equals 0, this term here would go away, so that would be dt dx at x equals 0 is equal to b. So in the end, Q dot in is equal to minus K A times B. And all of this information is given, so if you substitute, you would find that Q dot in is equal to 120 kilowatts. Okay, and then similar to that, dt dx at x equal 1 meter, here again, dt dx is this, given by this equation. So if we put 1 in there, then dt dx at 1 meter is just going to be b plus 2c. Okay, so here again, using Fourier's law, Q dot out is going to be minus K times the area times dt dx at 1 meter. So we got Q dot out, it's minus K times the area at x equal times area times dt dx at 1 meter. Substitute into there, everything's given. We would have Q dot out is minus K times the area times this up here, which is B plus 2C. Substitute into here, everything's given. All this is given. And what you will get is Q dot out is 160 kilowatts. Okay? So here again, we've got Q dot in and we've got Q dot out. Okay? So part B says, well, what is Q dot being stored? Alright, so you know from the first law that energy stored is equal to energy in plus energy generated minus energy out. Okay, we just know this physically, that's happening. Okay, so the question, we already have energy in, we have energy out, so we just need to calculate energy generated. And if you look back at what's given, let's see, Q dot generated was 1,000 watts per meter cubed. We got the area, we know the length, so we can calculate the volume and get Q dot generated. So energy stored then is equal to energy in, which we calculated here as 120 kilowatts, plus the energy generated, which was given as 10 watts, let's see here, 1,000 watts per meter cubed, and then times the area, which is 10 meters squared, times the length to get the volume, which is 1 meter. And then this is watts, we need it in kilowatts, so let's see here, 1,000 watts is a kilowatt. Okay, then minus the energy out, which was 160 kilowatts. Okay, so if you run the numbers, run these numbers through your calculator, what you will get is that the energy stored is minus 30 kilowatts. So what that means is we've got more energy going out than is coming in and being generated. So in other words, your object here, your geometry is cooling down. Okay? Alright, so what are we up to now? Part C? Yeah, part C says find delta T with respect to the temperature at x equals 0 and several other locations. So here's where we want to throw in the heat equation that we learned last time. If you recall from previous lectures, this was the general form of the heat equation for rectangular coordinates. So our problem is one dimension, only in x. So d dy will be 0, d dz is going to be 0. So it leaves us with three terms. The terms here in x, Q dot generated, and then over here on the right side, the change with respect to time. So let me rewrite this. By the way, the conductivity is constant, so I'm going to go ahead and pull that out of the problem. Okay. So what we'd have then is K times D squared temperature times temperature, or the second derivative of temperature with respect to x, plus Q dot generated is equal to the density times specific heat times the change in temperature with respect to time. Okay, so what we need to do here, this was the Q dot generated was given, So we need to take the second derivative of our temperature with respect to x. Okay, now we already did the first derivative right here. So if we took this again, second derivative, okay, well, the derivative of b with respect to x is going to be 0 plus, and we've got 2cx, so that derivative will just be 2c. So in other words, the second derivative of temperature with respect to x is just equal to 2c, and c is given, so if you plug the numbers in there, you get minus 100 Celsius per meter squared. Okay, so if we substitute back into this equation and solve for dt with respect to time, everything here is given, the density, specific heat, q dot generated, but if you did the math on that, you'd see that dt, the time, change in temperature with respect to time, is minus 4.69 times 10 to the minus 4th degrees Celsius. Okay? So, what this means is that the change in temperature with time is a constant. And notice it's not a function of x. So it doesn't matter what the location is. So at x equal 0.25 or x equal 0.5 meters, you'll get the same thing. Okay? Okay. So let's see here. Let me turn this thing around. I hope you can see me. That was an example using the heat equation through a rectangular wall for one dimension. And I'll work a few other of these, and I've also emailed you the solutions and the problems. So if you have any questions, you know what to do. I sent you that email, a special email that I set up in Yahoo. So you guys, if you have any questions, just let me know. I'll see you next time.